Okay, so welcome to the next video on functional analysis, where we're going to examine another metric space, and we're getting gradually more abstract. So we're going to go back to sequence spaces now, and we're going to look at a much less restricted class of sequences than we saw in the L infinity case. So firstly, let's start with our set that we're going to define this metric space on. So let S be the set of all sequences, so all x, which is an element, which is a sequence of numbers, xn, n is equal to 1 to infinity, and the xn's are going to be elements of the complex numbers. They're going to be complex numbers. So just to make give a concrete example, we could have x is equal to 1.3i, 1 plus 3i, 2, 4, 1, 8i, 7 plus 5i, let's say, 6 minus I, and you can go on and on and on. So they're just elements of the complex numbers, and these do not need to be the sequences which converge. They do not need to be sequences which are bounded. They are just sequences of complex numbers. They have no more fancy properties. So it's just, effectively, you can think of x as being a mapping. X is a mapping from the natural numbers into the complex numbers. So to every natural number, 1, 2, 3, 4, 5, 6, 7, it's going to ascribe a complex number as so. 1 goes to this, 2 goes to this, 3 goes to this, 4 goes to this, 5 goes to this, 6 goes to this, 7 goes to that. Okay? So that is what we can think of, what are sets that we are defining our metric on. So how do we turn this into a metric space? Well, we need to define a metric. So I need to define the distance between any two sequences, x and y. So let x and y both be elements of S. Then I'm going to define the distance between x and y to be equal to the sum I is equal to 1 to infinity of 1 divided by 2 to the power of I of xi minus yi divided by 1 plus xi minus yi. So that looks like something absolutely horrendous. It looks like some hideous thing from real analysis that we just do not want to look at, really. But it's not. It's not that difficult. It's a very nice way of defining a metric on it, and in my opinion, it's absolutely incredible that you can define a metric on a stupid space like this. This is a really silly set. These sequences do not have any nice properties whatsoever, so it's very nice that we can define a metric that is well defined and is going to obey the properties of a metric space. So firstly, let's make sure that it is well defined. So we need to make sure that this actually does converge on something, basically. The first thing to note is that each of these terms, for every I you plug in there, we're going to get a positive number. So we're adding up loads of positive numbers. So providing it's bounded, it's going to converge then, because remember what this means. It really means the limit as n approaches infinity of the partial sums. So it really means the limit of the partial sums. I is equal to 1 to n over 2 to the I xi minus yi, oh dear, what am I doing, over 1 plus xi minus yi. So it's the limit of, this is the sequence basically, it's the limit of the sequence of partial sums. And basically, basically, if you look at this, let's call this the sequence Sn, shall we call it? Yeah, we'll call it Sn. Or maybe something better, let's use a different letter. Let's call it Am, we haven't used A for anything. So let's call this sequence of partial sums An. So it's the limit as n approaches infinity of An. Well, I need some more paper. The first thing to say is that this sequence is monotonically increasing. So An plus 1 minus An is going to be equal to, so if you sum up to n plus 1 and then subtract off the sum up to n, it's just going to equal 1 over 2 to the n plus 1 x r n plus 1 minus y n plus 1 divided by 1 plus x to the n plus 1 minus y to the n plus 1. Now this is a positive number for all n. For all n, this is a positive number. So this, an plus 1 minus an, is greater than or equal to 0. In fact, it's greater than, strictly greater than 0, for all n is an element of the natural numbers. So it's a monotonically increasing sequence, this an. So if we draw it, it looks something like this. This is, let's say this is a1, so we've got 0 down here. Then we've got a2, a3, a4, and it goes on, a5. So there is a pretty simple theorem in real analysis which says that if this sequence is bounded, i.e. if there is some m up here, which is bigger than all of the an, so an is less than m for all n is an element of the natural numbers, i.e. absolutely every single term of the sequence is lower than this, that's what it means to be bounded, then the limit as n approaches infinity of an exists. And that's going to be very useful. That's a very, very useful fact about monotonically increasing sequences, which allows us to evaluate infinite series of non-negative numbers very easily. So the limit as n approaches infinity exists, so we'll call it a. So the reason that is true is if it's bounded, then if you take the set, let's say the set T, which is the set of ai, well, let's say an rather, for n is an element of the natural numbers, so if you put them all in a set, so you put every element of this sequence in a set, and then that set is bounded. It's a bounded set because all of the elements are less than n. So by the least upper bound property of the real numbers, the supremum of T exists, and that supremum is going to be greater than all of these values, but it's greater than, but it's the least value that is greater than all of them. So basically, that is what these converge to, because if you can imagine them getting closer and closer and closer to this supremum up here. Okay, if they didn't converge to this, if they didn't converge to this, then it would mean that there would exist a point basically closer. So let me just prove this quickly. I want to prove that sup of t is the limit of this. So what do I need to show? To show that I want to show that sup of t is the limit of an. So to show, for all epsilon greater than 0, I must show that there exists a big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies that an minus sup of t is less than epsilon. So if this is not true, so we'll do a proof by contradiction. Proof by contradiction. If it's not true, then so proof by contradiction. Suppose not true, and I want to move this up so that you can see it properly. Suppose that it's not true, then there exists an epsilon greater than 0, where there does not exist an n is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies an minus sup of t is less than epsilon. So there is no point. So if we draw a picture, sup of t, we have some ball epsilon around here. There is no point. There is no big N, which is an element of the natural numbers, such that little a of big N is within here, and any point beyond it is also within here. But that means that all of the little a n's cannot be in this interval sup of t minus epsilon to sup of t plus epsilon. The reason being that it's monotonically increasing. So if one of them, if even one little an, so let's call this little an, so if even one of the points gets within here, then all of them have to go within there, because all of them are greater, all of them afterwards. So if little n is an element of this interval, then it implies that little a n plus 1 is also an element of this interval, because little a n plus 1 has to be less than sup of t because it's an upper bound for this entire set, but it also has to be greater than a n, so it would be in here, and all points following would be in here, which would imply that it would be true that that there was a point big N, which is an element of the natural numbers, such that all the points after that are elements of this interval. So if that's not true, if we're assuming that it's not true, then it must imply that all of the points are outside of this interval, which means that they're below it. Which means that I can take any point of this interval, and that would still be an upper bound for the set T. So if I took this point here, let's call it P, then P would be an upper bound for T, for the set T, which is a contradiction because P is less than sup of T. So it would be a better choice for the least upper bound. So it would contradict sup of t being the supremum of t if sup of t was not the limit of this monotonically increasing sequence. And note that we used the fact that the sequence was monotone. If it's not monotone, then it is possible that there were points getting infinitely close to sup of t, but there wasn't any point a big N for which all the points after that stay within the interval, i.e. they could keep dodging in and out again, but the fact that it was monotone meant that they all had to, once they were in it, they had to stay in that interval basically, because they had to be bigger than the one previous. Okay, so we did use the fact that it was monotone. So basically what we have shown there is that all monotone sequences do have a limit, providing that they are bounded. Okay, so if we want to show that this great big that this sequence an has a limit, then since it's a monotonically increasing sequence, all we have to show that it's bounded by something. But that's quite easy, because if we remember, an is equal to this sum, I is equal to 1 to n of 1 over 2i xi minus yi over 1 plus xi minus yi. Okay, the modulus of xi minus yi. Well, the key thing to look at is this, xi minus yi over 1 plus xi minus yi. Xi minus yi, the modulus of that, the absolute value of that, is always non-negative. So we have this non-negative number divided by 1 plus this non-negative number. That is going to be less than or equal to, well, it's going to be greater than or equal to 0, but it's going to be less than, or it's going to certainly be less than 1. It can't ever get bigger than 1 because this thing is always going to be bigger than this. So you're always going to be dividing one number by something that's slightly bigger than it. So you're always going to get something less than 1. Okay, so that implies that 1 over 2i times this absolute value of xi minus yi divided by 1 plus the absolute value of xi minus yi is less than 1 over 2 to the 2 to the power of I. So it's less than if this thing was just on its own. Now, because of that, so I'm just going to rewrite out the result we just got. We got that 1 over 2 to the power of I times the absolute value of xi minus yi divided by 1 plus xi minus yi is less than 1 over 2 to the power of I. Now, if you sum up from I is equal to 1 to n of 1 over 2 to the I xi minus yi over 1 plus xi minus yi, and we're just summing up to a finite value at the moment, then it still holds that this is going to be less than the sum from I is equal to 1 to n of 1 over 2 to the power of I. So if you sum up loads of things that are big, basically what we're doing is we're summing up from 1 to n all of these, and all of these inequalities hold, and you can combine them together. It will be a bit of a nightmare to actually do, but from the axioms of the ordered field you can show that this implies this. But intuitively it's pretty obvious that if you sum up a bunch of numbers and you sum up a bunch of numbers that are bigger than each one of these, so each of them has an analogous friend in here, and it's bigger than that friend, then so let me give you an example. So if we have if we have husband and wife, and the husband is always bigger than the this is really sexist, but if we assume that the husband is bigger than the wife, and we lie down all the husbands in a long great row, n husbands in a head, line them up, foot to head like that, and then we have the wives here, and the wives are always shorter. Then overall, the length of the wives is going to be less than the length of the husbands, basically, is the intuitive sense. I'm sorry if I have offended anyone with that crude reasoning there. Okay, so on the other hand, this is absolutely true, and it does follow from the axioms of the ordered field. Okay, so if we take the limit of, as n approaches infinity, of a sequence an, and we have that the sequence an is always less than or equal to the sequence bn, then we do know that the limit as n approaches infinity of an is less than the limit as n approaches infinity of bn. Again, that's a basic fact from real analysis. So both of these have their limits existing, so we can take the limit as n approaches infinity of this side, so limit as n approaches infinity of this side, so of the sum I is equal to 1 to n of 1 over 2 to the I xi minus yi. Keep wanting to do that. 1 plus xi minus yi, the absolute value of that, is therefore less than the limit as n approaches infinity of the sum I is equal to 1 to n 1 over 2i. Now we know what this is. This is the sum of a half plus a quarter plus a eighth plus a 16th. So if you think about having a square, a 1 by 1 square, you add on a half, you add on a quarter, you add on an eighth, you add on a 16th, you add on a 1 over 32th, etc. You go on and on and on, and eventually you're going to fill the square, and this limit converges on 1. So we get that this great big this limit of these partial sums is less than 1. So we have a bound for this monotonically increasing sequence, so therefore its limit does exist. So this exists. So the function is well defined. The metrical function defining d between x and y to be equal to the sum from I is equal to 1 to infinity. And recall that when I write I is equal to 1 to infinity, what I really mean is the limit as n approaches infinity of the partial sums. 1 over 2 to the I, the absolute value of xi minus yi, divided by 1 plus the modulus of xi minus yi. So now we're going to go on. We're going to now make sure that this is a metric space. So axioms of metric space. So the first axiom of metric space is that the distance between x and y should be an element of the non-negative real numbers. Well, we're adding up a bunch of non-negative things. So each of the terms in this sequence, if we sum up just to if we view it as the limit of the partial sums, then each of the partial sums is going to be a positive number. So it most certainly converges on a positive number. So that's checked. 2, that the distance between x and x is equal to 0. So the distance between x and x, by definition, is the sum from I is equal to 1 to infinity of 1 over 2 to the I, xi minus xi, divided by 1 plus xi minus xi. Now xi minus xi is 0 for all I. So that's going to be 0. The more absolute value of 0 is 0, so we're going to be multiplying each term by 0. So we're going to be taking the limit as n approaches infinity of the sum from I is equal to 1 to n of zeros. So that is just the limit as n approaches infinity of a continuous string of zeros, and the limit of a continuous string of zeros is 0. So very good. We have that the distance between any two identical sequences of complex numbers is 0. Great. Okay, so now let's check it the other way, that if the distance between x and y is equal to 0, that implies that they are identically equal to one another. So if the distance between x and y is equal to 0, that implies that the sum from I is equal to 1 to infinity of 1 over 2 to the power of I, xi minus, oh dear, what have I, oh no, that's fine, xi minus yi, over 1 plus the absolute value of xi minus yi, is equal to 0. Well, this is a monotonically increasing sequence. So if we view it as the limit as n approaches infinity of the partial sums up to n, each of those is monotonically increasing. So the only way that it can possibly converge on 0 is if all of the terms are actually equal to 0, because none of the, if you view it as the limit as n approaches infinity of these partial sums, I is equal to 1 to n, of 1 over 2i, the absolute value of xi minus yi, 1 plus xi minus yi, then the n plus 1th term is going to be greater than or equal to the nth term. That's what it means to say that the sequence is monotonically increasing. So the only way that it can possibly converge on 0 is if absolutely every single term remains as 0. And the only way that can happen is if every single one of these terms is 0, because if the first term, if you sum up from n is equal to 1, then that will give you just this sum from n is equal to 1, 1 over 2 x1 minus y1, the absolute value of that, over 1 plus the absolute value of x1 minus y1, and then if you go up to 2, it will give you another one. But if the first one was equal to 0, then that new term that you added on, the 1 over 2 to the 2 plus times x2 minus y2, the absolute value, over 1 plus the absolute value of x2 minus y2, that would have had to be equal to 0. So this implies that 1 over 2 to the I xi minus yi over 1 plus xi minus yi is equal to 0 for all I is an element of the natural numbers. Okay, so the only way that this can happen, 1 over 2i is never equal to 0. 1 over 1 plus xi minus yi is not going to equal 0. So this front term here has to be equal to 0. So xi minus yi must equal 0 for all I is an element of the natural numbers. So this implies that xi minus y is equal to 0, which implies that xi is equal to yi for all I is an element of natural numbers, which implies that yes, x and y were identically equal as far as the sequences were concerned. Okay, so now let's prove this basic, the most easy one, the symmetry property. So 3 is symmetry. Now the distance between x and y we know is given by the sum, I is equal to 1 to infinity, so the limit of the partial sums, 1 over 2i, the absolute value of xi minus yi, divided by 1 plus the absolute value of xi minus yi. But again, the absolute values do not care whether you take the absolute value of xi minus y or the absolute value of yi minus xi, so we can replace this by the sum from I is equal to 1 to infinity of 1 over 2 to the I of yi minus xi over 1 plus yi minus xi. Okay, so this is then equal to the distance between y and x, so it is symmetrical. Now, finally, we're going to do the triangle inequality, and this is the only non-trivial one, triangle inequality. Okay, so this looks like a bit of a monster to do, but there is going to be a nice trick that is going to help us solve this problem. And basically what we're going to do is we're going to look at the function f of t. F of t is equal to t over 1 plus t. And basically this function, if we plot it out, there's another way of writing it, which is if you imagine adding 1 onto there and then subtracting 1 off, then the 1 plus t here cancels with the 1 plus t there, and we get that it's equal to 1 minus 1 over 1 plus t. So this is quite easy to plot, because if you plot 1 over 1 plus t, that looks like 1 plus t. So we're going to shift it by negative 1 is going to go to the equivalent position of 0. So it's going to look like this with the asymptotes at negative 1. Oh, sorry, no, it's not going to look like that. It's going to look like this. I was writing the negative of it. So if we take the negative of 1 over 1 plus t, that is going to look like the negative of that. So flip it in the x-axis, and it looks like that. So we get that we get that it's it's flipped like this. So if we add 1 to that, if we take the function 1 minus 1 plus t, 1 plus minus 1 over 1 plus t, then this is just going to raise it up by 1. So it's going to look something like that, and it goes perfectly through the origin, which you can check by just sticking in t is equal to 0 there. And it's going to look something like that, So we'll continue this discussion in the next video.